All right, let's dive in. If you've ever been in a tech interview, you've probably run into a problem that looks simple but hides a super elegant, optimal solution. Today, we're going to tackle one of those classics, the sorted squared array problem. So let's break it down. So here's the deal. We get an array of integers, and it's already sorted. Our job, take those numbers, square them, and spit out a new array that's also sorted. But here's the real kicker, the constraint that makes this interesting. We're not allowed to just square everything and then hit the sort button. We have to do this in what's called linear time, or O of n. Okay, so let's talk about the first thing that probably pops into your head, the naive approach. And look, it makes perfect sense and it totally works, but it's a classic interview trap because it kind of misses the whole point of the puzzle. So where's the trap? Well, it's all about those pesky negative numbers. Just look at this example here. You take a sorted array like -3, -1, 2, you square its numbers and you get 9, 1, 4. And boom, the order is completely shot. Why? Well, because that little -3 on the far left, when you square it, becomes 9, the biggest number in the new set. And that right there leads us to that straightforward two-step naive solution. Step 1, you just loop through the original array and square every single number. Simple enough. Step 2, you take that messy, jumbled up result and just run a standard sorting algorithm on it. And yeah, it gets you the right answer, but at what cost? And here's the final judgment. It's just not optimal. You see, that sorting step, that costs you O of n log n time. We can do so much better. The biggest mistake, the real crime here, is that this whole approach just throws away the most valuable clue we were given. The input array is already sorted. That's a huge hint we need to be using. Okay, this brings us to the core insight, the aha moment. This is where we're going to pivot from that slow brute force method to something way more clever and way faster just by looking at the problem a little differently. And you can see the key insight perfectly visualized on this graph of y equals x squared. It's a classic parabola, right? Just notice how the curve shoots up, way up on both the negative and the positive sides. This simple shape tells us everything we need to know. The biggest squared values? They are always going to come from the numbers that are furthest away from 0. So in our sorted array, where do we find those numbers? You got it, at the two ends, the extremes. Okay, so how do we take this cool insight about the extremes and actually turn it into code? Well, we're going to use one of my favorite, most elegant patterns out there, the two-pointer solution. Let's see exactly how this works. It's pretty simple to set up. We're going to have 2 pointers. We'll put a left pointer at the very beginning of the array and a right pointer at the very end. Now, at every step, we're not comparing the numbers themselves. Nope, we're comparing their absolute values. We just ask a simple question. Which of these 2 numbers is further from 0? Whoever wins that contest is going to give us our next largest square. Okay, now here's a really important part of the strategy. Since we're finding the biggest squared values first, we can't just stick them at the beginning of our new result array, right? That would be backwards. To get a final perfectly sorted array, we actually have to build it in reverse, filling it up from the end to the beginning. All right, let's walk through an example. So our left pointer is at -7, and our right pointer is at 30. We compare their absolute values, so that's 7 versus 30. 30 is clearly the winner, so we square 30, we get 900, and we pop that right at the end of our results array. Then we just scoot the right pointer one step inward. Okay, let's fast forward a little bit. Now our pointers are sitting at -7 and 1. So we do our comparison again. Absolute value of -7 is 7 versus 1. This time, the left side wins. 7 is bigger. So we square -7, we get 49, and we place that in the next empty slot from the right. And this time, it's the left pointer that moves inward. And this is how we so brilliantly handle those tricky negative numbers. And we just keep doing this over and over. Compare, square, place, and move a pointer. We do this until our 2 pointers finally meet or cross each other. And by the time we're done, what do we have? A perfectly sorted array of squares. The most important part is that we only had to look at each number one time. That's a single, super efficient pass. And this is what it all looks like when you put it into code. You can see all the key parts right there on the screen. We pre-allocate our result array, which is good practice. We have that reverse for loop that lets us fill the array from the end. And of course, the heart of it all, that simple if statement comparing the absolute values. It's so clean, so concise, and just blazing fast. All right, so let's check the scorecard. For time complexity, we're looking at ON, a beautiful linear time because we only make that one pass. Space complexity is also ON, and that's just because we have to create a new array to store the results.
I mean, this is a huge, huge improvement over that slow O(n) log n naive approach. Mission accomplished. We've found the optimal solution.
What really makes this algorithm so great is just how robust it is. Because the whole thing is built on comparing absolute values. Who's farther from zero? It just doesn't care if the array is all positive numbers, all negative numbers, a mix, or even just a single number. That two-pointer comparison logic just handles it all perfectly, every single time.
Okay, but the most important thing to take away from this isn't just the answer to this one problem. It's really about recognizing the pattern underneath it all, the two-pointer pattern. This isn't just some one-off trick, it's a fundamental, reusable technique you should have in your back pocket for interviews. So, when should your brain start screaming two-pointers? Well, look for these key ingredients. You've got a sorted array, the problem is asking you to find pairs or do something with the extremes, and the goal is an optimal O of n solution. You're going to see this pattern pop up all over the place, in famous problems like two-sum, container with most water, even checking for palindromes. So, next time you're in an interview and they hand you a sorted array problem, I want you to remember this little mantra. Recognize the sorted property, exploit the extremes, and meet in the middle. It's a really powerful way to think that just unlocks these kinds of optimal solutions. The only question left is, what else can you solve with this?